All right, let's begin. Let me just make sure that you can hear me. Let me know. Okay, is the audio okay? Can you hear me? Okay, good. It's a little bit difficult to judge because from here I don't hear those speakers as much as you do. All right. So I apologize for 2 weeks in a row of online lectures. Nothing I could do about it, but you know, understand how difficult it is to concentrate fully on your lectures when they are online. So let's try to get back into the swing of things. For all of you who missed some of the lectures, remember that you can, like, whatever you missed, you can catch up on using slides. So actually, it shouldn't be a big problem if you missed like a couple lectures. You can just go through the slides, or you can go through lecture recordings. That's just to, you know, remind you that if something went by, you don't need to worry that now there is no chance to catch up. This, at least, like, the slides are designed in such a way that you should be able to catch up, even if you missed a lecture. All right. Now, with that, let's go to today's topic. And today's topic is discrete control. So let me remind you quickly, like, where it is in the big picture. So we already know representations, right? Like, we know what systems we control. Especially on tutorials, you've seen a lot of mechanical systems. If you go to, like, other textbooks, you will see electrical systems. Those are the things that we control. We know how to represent them. We know how to make state space models from ODEs. We know how to write transfer functions. And we know how to analyze them, right? We know how to do stability analysis via eigenvalue analysis. And we know how to analyze their reaction to inputs via, for example, Bode plots. If you know transfer function, you can easily see how the system will react to different frequencies, right? So that is what we studied. And last lecture, we also studied how to control systems. So we studied how to design a controller that would make a system that is inherently unstable stable. Okay, so that is where we are. Now, what we didn't say so far was the fact that we were implicitly talking about continuous time equations. So continuous times dynamics. What do I mean by continuous time dynamics? Well, we assumed that the dynamics depends continuously on, is there some light problems? Yeah, I mean, otherwise we wouldn't see the blackboard, right? Give me a second. Okay, is that fine if we keep it on? Is it, or is it not? Okay, is that better? Okay, good. I'm just worried that you wouldn't be able to see like well on the blackboard. Okay, sorry about that. All right, so we were implicitly talking about continuous time systems. What is continuous time? Well, like, one way to think about it is to say, okay, here's the equation. The solution to this equation is something like this. Right? And this solution exists for any t on the continuous spectrum. Okay. So this is one way to think about it. And that is continuous time, because you can put any t here. And that is one way to think about it again. Any t here, and you'll get some result. Another way to think about it is you can always find a derivative of x in any at any point of t, x star at any point of t. So continuous time. And that is pretty much the equations, differential equations that we studied in in university course, right? Like in your OD course, it always looked like this, right? However, in practical electronics or computer-based, tech, you don't get to use continuous time very often. Why? Well, for example, let's say that your control loop runs on, like a realistic processor. Let's say your control loop has 100 lines of code, and this 100 lines take 1 millisecond to run. That is quite long, but just let's say 1 millisecond. So how often can you, at which frequency can you run this code? How many times per second can this update? 1,000, right? So 1,000 hertz, that's 1 kilohertz. That is what we call it. So basically your code cannot possibly update faster than 1,000 times a second. So let's say that you have a process where you have a control that is written like this. Last lecture, remember, right? State times control matrix gets output, except it is only updated 1,000 times a second. So let's let me rewrite it a little bit different. Let's say it is minus k x minus x star. That is what we wrote last time when we discussed error dynamics, right? Where error is it x minus x star? Yeah, I think so. Let's just write it like this. Doesn't really matter. Okay, so this is what we saw last time, right? Your control depends on gain times error. Okay, but this guy is a function of time, right? Is a solution. Like it's some kind of solution. So actually you can write it like this. Okay. But if this control loop actually only runs on 1,000 times a second, it means that you don't get here like a continuous function of time. Instead, you get x star at the moment 0, at the moment 0.001, 0.002, etc. Right? So it's you evaluate it at some sample points. This guy, x, current state, actually you get it from measurement. Like how else would you know your current state? You have to measure it. We didn't discuss it, but let's believe me for now. You get it from measurement. You measure your current position, your current velocity, etc. And that also requires time. You cannot do it infinitely fast. So what happens is you have here time as well, right? Usually it also has some lag because the measurement happened a while ago. It took time for it to process. So there is a lag, but let's leave it, out of discussion for now. So what I'm trying to say here is that your control is a function of time, basically, right? And if you can update it only 1,000 times a second, that means that your control output, instead of looking like this, where x times mk, x is some smooth function, u is a smooth function. Instead, it actually looks maybe something like this. Here I'm oversimplifying maybe a little bit. Maybe your control looks like this, right? So what I'm trying to say is your control, the shape of the actual function wouldn't be smooth if you run it on a computer, because your computer cannot produce smooth outputs because of the finite frequency of your at which your program runs. Right? You compute each individual point using some sort of a code expression, and this point stays the same for as long as this code runs. So if this is 1 millisecond, this is what happens, right? Your output stays the same for 1 millisecond, because that is how long it takes for you to update your code. Did you get the idea? All right. So because of the way computers work, you can expect your output to be this staircase function instead of looking like smooth. There is another aspect to it, which we are not going to discuss, but it is quantization. Computers have finite precision. So instead of, for example, having, let's say, allowing any numbers, they allow only, like, let's say, reals, integers, doubles. And if you had a course on C or something like this, you probably know already what a float, what a double precision, what the integer precision is, right? It's how many bytes you have to store the number. So that is also an effect. And this becomes much more potent when we start talking about measurements, because measurements are usually don't allow you a lot of precision. The reason I'm bringing this up is because there are two twin terms that you would find if you talk about computer technology: quantization and discretization. Quantization is when you have a fixed ladder upwards, right? If you have fixed steps upwards, you cannot go more fine than a certain discrete unit, right? So, for example, you can have a value, let's say, just as a very crude example, you have this, can have this value, can have this value, but you cannot have, for example, this value. That would be an example of quantization. If your quantization step is 1 over 1,000. Usually quantization step is some sort of a power of 2, but you know, that is the idea. Discretization is when you say that you can evaluate something at the moment of time 0, at the moment of time t, at the moment of time 2t, but not between those. So the quantization is in value, discretization is in time. That is quite confusing because you know, the word discrete, you know, it just kind of implies every, like this, you know, like this step upwards. Also, you can say it is discrete step, right? But discretization is specifically talking about time. All right, sorry for this aside. I just wanted to make sure that we understand the words. Discretization in the control theory specifically refers to discretizing the time. So when you chop the time into finite steps. Now, today's lecture will be about that, about how we deal with chopped time. And maybe, you know, at this point, after this kind of like introduction, what you think is, okay, that's like such a specific topic, is like in a specific course, definitely not very interesting. Let me just tell you one thing. Every control system runs on discrete, like in discrete mode. Because continuous systems don't, you know, are not compatible with computers. You can use continuous control to design something meaningful, but at the end of the day, your control system will run like a discrete control system. You would have to somehow connect. So continuous control is great for a variety of reasons. But in practice, you'd find it very difficult to see a system where you don't take into account discretization of time. Okay, and definitely all modern systems such as quadrotors, walking robots, cars, etc., all of them run on discrete time, because the amount of processing for each step is huge. So the frequencies are also quite low, like kilohertz, not like hundreds of kilohertz, but kilohertz, and that is very discrete. So, you know, content of this lecture extremely applied for everything related to reality. Okay. Now let me show you. Yes. Discrete. Okay. So if you want to have a rule of thumb about if you should consider your system as continuous or discrete, I would recommend to, instead of thinking about it this way, to simply, how should I put it? When you encounter a practical problem, look at it, notice that the frequency is somewhere below 10 kilohertz, and consider it discrete. When you encounter something when the frequency is higher than 10 kilohertz, like then study the problem carefully, because probably what you need to think about would be not the discretization problems, but some other issues. Because whenever something runs on extremely high frequencies, there are usually other considerations than representation that you have to take into account. That sounds very kind of like arcane, instead not clear for sure. But the practical examples of systems that run on extremely high frequencies are either very precise mechanics, which is not something that you can tackle without knowledge of the subject, or electronics, where again, a lot of subject knowledge is required, or embedded systems for like motors and other servo systems. So like small units. Again, they usually have subject-specific things to think about. So the way you represent your system would not be dictated so much by continuous versus discrete as by specificity of the problem. So what I would recommend, again, is just to look into your problem, see that the frequency is actually quite low, and just treat it as discrete. Or if you do it in purely in simulation, if you simply want to understand how to control something without implementing it, just go continuous. So that would be my suggestion. All right, but yeah, when you do start engineering practice, a lot of this will become clear from the practice, not from lectures. Okay, so this slide represents how we think about discrete systems. So first equation is a discrete state space equation. Please notice that I can call it ODE if I want to, but this is not a differential equation in the way we understand it, right? That is just an algebraic expression. That just tells me what x plus 1, I plus 1 is based on the x sub I and u sub I. What is x sub I? It's a state at the moment I. We can say it is a x sub I is a state of the system at the moment t sub I. And I is 1, 2, 3, 4, 5, 6, 7. U sub I is a control applied at the moment t sub I. This doesn't look like a differential equation. And indeed, it is, we sometimes call it a difference equation. But I don't think introducing a term like a difference equation clarifies anything. But, you know, maybe at the end of the lecture, you'll see where it comes from at least. So it is algebraic. Algebraic is kind of nicer than differential, right? Like the algebraic equations, you solved them when you were in high school. So it kind of sounds like something maybe is going to become easier. What is fascinating about this topic is that some things are easier, but some other things here are more complicated. There are problems that you can solve in continuous time when you work with ODEs, but cannot solve here. So, you know, let's respect the problem for now. Right? It is difficult. Equation number 2 is how we design control. It's exactly the same as before. We take some matrix, multiply it by state, add constant component if we want. What I try to impress with this slide is that it is quite similar to what we saw before, but instead of x dot, we have x sub I plus 1. So the next state can be directly computed from the previous state. You don't need to solve Cauchy problem or anything. You just take your state, multiply it by a plus bu, and you get next state. That's all. All right. Looks nice. By the way, simulation is that is how you simulate it. You don't need to call ODE int or whatever. You just simulate this way. Yes. No. It is. That is interesting. Like the way you think about u and this I variable is dictated either by definitions or by practice, right? And so if I can just tell you, no, it is like this is correct. What you propose is correct, right? But there is a reason for that. So, for example, why is it here not u sub I plus 1? Why not u sub I plus 1? Well, think about it this way. Let's say we have at the current step t sub I, we have our x sub I measured. Let's say we so at this point, like we have a processor. The processor has measured state. Okay. So we have x sub I. We also have, let's say, all right, here we don't have this part, so I would leave it away. All right. So we can compute some u, which is equal to minus kxi. How would you call this u? Well, this is a u that you computed at the time t sub I. We're not going to discuss how much time it took from computing from knowing x to compute u, because this time is probably negligible. Like the time to compute this expression is probably nanoseconds, maybe like 1 nanosecond, maybe more. Like it is negligible. The whole time is going to be spent computing x. Like measurement usually takes a lot of time, not the linear computation. There are other things. So it kind of makes sense to say that this happens at the same time slot as this. And then you can expect that on the next time slot, you would see something like this. But of course, that's what you expect. What actually is going to happen is what you measure, because of disturbances. But we didn't discuss a lot about measurements versus reality so far. So don't sweat it. But what I'm trying to say is that if you had this on the ith time slot, this also pretty much happens on the ith time slot. Okay, good question. Yes. Come again. What you mean? U is a control input. So let's say for remember last lecture, right? We discussed how we go from this to this, right? This is a control. We can set it something like this, and we'll go here. What it means in practice is, for example, for a motor, it will be how we design voltage applied to the motor. For a quadrotor, it is thrust of the quadrotor. For a rocket, it will be the direction and thrust of the engines. For a car, it will be the speed of with individual what do you call it? With electric car, for example, it will be individual motors, the torques that they apply on 2 wheels. For a normal car with one motor, it will be the steering wheel position and the speed at which it rotates the wheels. etc. Right? So U depends on the system, but basically that is something that we can control. Okay. Good question too. Any more questions? All right. Good. So as I said, the simulation here is very simple. You just simply run this. You don't need to call ODE int. That is important. We'll ask you to simulate, I believe, those systems at the homework. And that's pretty much all you need to do. Just run it in a loop. Okay. Now let's discuss stability. So we'll discuss stability in exact same terms as we discussed it for previous time when we discussed stability for continuous systems. And for that, we will drop control. As you remember, if you have U, you cannot really discuss stability, right? Like we need to have autonomous system. We cannot discuss stability of a system with external inputs. I mean, we can, but it becomes convoluted. Like we need to say what exactly we mean. Okay, so autonomous system, expression 3. As before, let's assume that we have Eigen Decomposition. That is a special case. That is not a general case, but it helps. It helps to understand. So Eigen Decomposition of the matrix A. So let me write it somewhere here. I'll duplicate a little bit of the slides just so we can understand it better. So let's say matrix A has a real eigenvalues, strictly real. If it has strictly real eigenvalues, and also that it has, I mean, we can just say, we assume that it has this decomposition, right? For this decomposition, where D is real, it has to have strictly real eigenvalues. It also would have, I believe, some additional requirements, but you know, just yes. So we're just assuming a special case when you can decompose A in this format, where D is a diagonal matrix of real eigenvalues and V are eigenbases. Yep. Not every matrix has this decomposition. I'm sure that I'm not sure if even if every matrix with real eigenvalues would have this decomposition. So that is, you know, that's something for you to think about. The decompositions, like in general, has a lot to do with Jordan normal form. So if you want to deep dive into which matrix has which decomposition, just brush up on Jordan normal forms. They have to do with like existence of those decompositions. All right. Anyway, assume that you have this decomposition. Then you can write expression 4. Expression 4 you can see is just we decompose and we substitute. And then next step, as before, we denote Z as Vx. Z sub I is Vx sub I. This is a standard way we do it. We did on the stability lecture. And we multiply both sides by V. So we have Vx dot, not x dot, Vx sub I plus 1 equal to V minus 1 d Vxi. This is Zi. This is Zi sub I plus 1. And this is identity. That is how we get to the expression 5. You get the idea, right? We already did it before, but I want you to understand how it came about. So this is the power of this decomposition. If it exists, we can just do this process and we arrive at expression 5. Expression 5 has a diagonal matrix. D is a diagonal matrix. So basically it means that it is a system of independent equations. Like first equation in this, like when you multiply diagonal matrix by Z, you'll just get like, you know, expressions of this kind. Z sub G I plus 1 equals to lambda sub G times Z sub G, right? I. So it just like you open the like you go from vector notation to scale notation. It just decomposes into independent equations. Is that clear? Okay. Now looking at the expression on the bottom of the slide, let's see if it is written out on the next slide. Yeah. What we can discuss is how the norm of Z changes with time for this scalar case. How does it change with time? Well, let's just divide Z sub I plus 1 by Z sub I. We can do it, right? Scalar. Since it is scalar, we can always divide it as long as x sub I is not 0. But if x sub I is 0, then x sub I plus 1 is 0, and the, like, you know, basically, like we don't need to. 1 second, I will take your question. If x sub I plus sub I was 0, we can assume that all subsequent Z will be 0. And the ratio, you know, we don't need to discuss it in terms of stability because it is stable, right? Like a sequence of 0, 0, 0, 0 is stable in the sense of Lyapunov. You remember what it means to be stable in the sense of Lyapunov, right? That we don't diverge. A sequence of zeros does not diverge. So this definition kind of looks like it will break when Z is equal to 0. But we just abandon this definition for this case and simply state that it does not diverge. Yes, one question. Yeah, that's why I was asking before. So let's consider Z1 sub I plus 1, Z2 sub I plus 2, plus 1, sorry, equals to, let's say, 2 and 0.5. So this I index means the point of time. 1 and 2 means which like components of Z. Okay. The same thing we can write as ZI plus 1 vector equals to 2, 0, 0, 0.5 ZI. You get the idea, right? Okay. So this we can transform into two equations. First equation is this. Second equation is this. Okay, let me check that people can actually see it on the camera. A little bit this way. Okay, I'm not sure if it is if people can see it, but you see the idea, right? So this is this would be an example. Now, what would be expression 6 now? We want to see the ratio between this variable and this variable. Well, Zi sub I plus 1 divided by Z1 sub I is equal to 2. And here, the same ratio is 2 sub I plus 1 divided by Z2 sub I is 0.5. All right, so those are the ratios. So why did we want to compute this ratio? Well, first of all, let me state that this ratio is eigenvalue, right? Because it was from Eigen Decomposition. This was Eigen Decomposition, and those numbers are eigenvalues. Okay. Second, why did we want this ratio? Well, if this ratio is bigger than 1, then each subsequent z is bigger than the previous one. Does it make sense? Okay. If it is smaller than 1, then each subsequent z is smaller than the previous one. Remember that Lyapunov stability is all about convergence. So if each subsequent z is smaller than the previous one, the sequence converges. Is that correct? Converges to 0, actually. If alpha is strictly 1, it means that the sequence does not diverge. So it is marginal stability, stability in the sense of Lyapunov. In fact, let me now repeat the final answer. If all eigenvalues of this system are smaller than 1, z converges to 0, and that is asymptotic stability, because it does not just not diverge, it is converge. It converges to 0. If at least one eigenvalue is bigger than 1, it diverges. Doesn't matter what others do. It's sufficient that one component diverges. All right. If all eigenvalues are less than or equal to 1, and for example, one of the eigenvalues is 1, then it is marginally stable. It does not converge to 0, but does not diverge either. For this case with real eigenvalues, okay? But remember, eigenvalues can be complex. So real eigenvalues is just a special case. But for real eigenvalues, we found the answer already. Actually, it will be the same answer for complex eigenvalues. It's just that this is clear how we derived it. For complex, it's not going to be as clear. But let's just see. So consider the complex case, the same as before, 2 by 2 case. What you see here is a 2 by 2 system where x sub I plus 1 is equal to this matrix alpha minus beta alpha times x sub I. We can find norms of those two vectors of x sub I and x sub I plus 1. So the norm of the first vector is just square of the first component plus the square of the second component. I find the square of the norm, not the norm itself, but the square. So to avoid square roots. But you know, that is of no consequence. Okay, norm of the second vector, x sub I plus 1, is what I've wrote there, alpha squared plus beta squared. How did they find it? Well, let me, I guess, write it out. But the process, you can kind of imagine how I did it, right? We have x sub x1 I plus 1 is equal to alpha x1 sub I believe minus beta, right? Minus beta x2 sub I. x2 sub I plus 1 is equal to beta xi x1i plus alpha x2i. Is it correct? Yeah, it is correct. Now, what do I do to find the norm of this? Oh, just square this plus square this, right? So let's find the square. I'll open the brackets at once. It will be alpha squared x1i minus 2 alpha beta xi1 x2i x1i x2i plus beta squared xi x2i plus this squared beta squared x1i squared plus alpha beta x1i x2i plus alpha squared x2 I squared. Please notice that we have a minus sign here. Minus sign here, plus sign here, and the same expression. So this cross term vanishes. It is the same here, but with different signs, so it vanishes. So what we have here is alpha squared appears twice in front of x1i and x2i. Beta squared appears twice in front of x2i and x1i. So we can get it out of the brackets and we get this expression 9. Good, right? Now we want to find the ratio between those two square norms. Remember, if the let's just find the ratio. Okay, so the ratio is this expression alpha squared plus beta squared. Why? Let's just look for a second back. The first norm is this. The second norm is the same, but times alpha squared plus beta squared. Satisfied, right? Like you see what's going on. Okay, now the ratio is just alpha squared plus beta squared. That, remember, is a ratio between the squares of the norms. Okay. By the way, I think expression 11 is a mistake. It shouldn't be norm of lambda. It should be, I think, norm of lambda squared. So this, let me write it somewhere here. What we found is the ratio of the squares of the norms. I think it is kind of clear that if the ratio of the squares of the norm is bigger than 1, then the ratio of the norms is also going to be bigger than 1. But let's just write it out. I mean, I don't know. If this is the case, then we can safely say that this is the case, right? This implies this. So we found that the ratio of the squares of the norms is lambda squared. Then the ratio of the norms themselves is just lambda by, of course, lambda, but by absolute value. Lambda in this case is the eigenvalue of the system. What is the eigenvalue of the system? Eigenvalues of the system was alpha plus or minus j beta. Alpha plus or minus j beta. What is lambda by absolute value? What is the square root of alpha squared plus beta squared? So you can see this is indeed the ratio of the norms. The ratio of the squares of the norms was alpha squared plus beta squared. The ratio of the norms, if square root of that, is just the absolute value of the eigenvalue. I'm sorry if this is a little bit pedantic, but I want us to understand where we get those ideas from. So what I'm trying to say here is, again, the square is missing from the expression 11. Is that in the complex eigenvalue case, for 2x2 system, you would have the norm shrink if the eigenvalue by absolute value is less than 1. Before, remember, for continuous time case, what we cared about is the real part of the eigenvalue. The real part had to be less than or equal to 0. Here, we care about absolute value of the eigenvalue. It has to be less than or equal to 1. And the reason is a shrinkage of the norm. That is for 2x2 case. Now, I don't think I will have a slide on other cases. Let me just check. Yeah, so I'm just stating the final result without showing you how you can extrapolate to any cases, but the argument is exactly the same as in the continuous time case. You just assume that you have a decomposition in a complex eigenvalue decomposition. And if it exists, then you can directly use the previous results to prove everything. Of course, it doesn't have to exist. Like, that's the catch. Again, if you want to complete treatment, go for Jordan forms. Like the complete treatment of stability analysis is done by going through Jordan form decomposition. It's very interesting, but as far as I remember, it's quite clear. You know, like the additional hoops are not so bad. Okay, good. So the final result is discrete systems, linear systems, are stable, asymptotically stable, if and only if eigenvalues of the system, all of them, are less than or equal to, or strictly less than 1 by absolute value. They are marginally stable if at least one eigenvalue is equal to 1. They are unstable if at least one of the eigenvalues is bigger than 1. Okay. Let me show you something that is, I think, good pictorial example of what's going on with eigenvalues of continuous and discrete time systems. So let's say this is eigenvalue plane. This is a real part. This is imaginary part. Okay. This is a complex plane. So for continuous time systems, this is the part where the system is stable. Right? And this is the part where the system is marginally stable. You get the idea, right? This is where for continuous time systems, this is where real parts of the eigenvalues are 0. This is the part where the real parts of the eigenvalues are negative, so stable. Okay. Now for discrete time. For discrete time, we'll draw the same diagram here. Real, imaginary. But now it is the stable part is actually a circle with a radius 1. That is a stable part. At the boundary of the circle is marginally stable systems. Continuous case is x dot equals to ax. Discrete is x sub I plus 1 equals to ax sub I. We're talking about the eigenvalues of the A matrix, right? Of course, they are not the same. Like if you discretize this system, and what I mean by discretize will be clear in a couple slides. But this matrix and this matrix do not represent the same system at all. Like they're completely different. Is that clear? Okay, good. That is the interesting picture to have in mind. So here, for discrete case, what you want is to drag your eigenvalues towards 0. For this case, you want to drag your eigenvalues towards minus infinity. Okay, but remember what I said, right? Every system can be represented by, I mean, more or less, by ODE. But practical systems run in discrete time, so we represent them by those equations, difference equations. but we're talking about the same systems still. But in one case, eigenvalues, we want them to be minus infinity, or, you know, we don't really want minus infinity. We want just big minus number. And here we want 0, close to 0 if possible. We don't want actually 0 here because that would be impossible, right? It would mean in one click it goes to 0. Here we don't want minus infinity because it would mean like the error falls like a cliff, like from a cliff. That's not realistic. Non-realistic, minus infinity non-realistic, 0 non-realistic. So we don't actually want that, but you know, that's kind of like direction. Okay. I propose we'll have a 5-minute break, and then we'll continue with the second half of the lecture. How much time do we have? We have about half an hour, right? So 5-minute break. Okay, good. Now, let's try to now understand where discrete systems come from. We understood how to analyze them. By the way, from understanding how to analyze them, we automatically understood how to control them, right? Because pole placement, I don't know if you already tried it on your practice, pole placement. Basically, this. I remember during the lecture I told you that there is this instrument that basically you can call in Python or in MATLAB something like place, and you tell it A, B, and your eigenvalues. Yeah, yes. So A, B, and alpha. Like if you just give it your desired alpha, just give it alpha that you want to be less than by norm less than 1. Let's say give it alpha like 0.5, 0.2, 0.1 plus j 0.1, and would stabilize the discrete system, right? So there is nothing different about the control design. Alpha and beta, A and B, just A and B matrix, and all you want is for the closed loop to have this property. Let me show you. So this property, stability property, is should hold for the closed loop. Let me remind. So, okay, let's just treat it for a second. So you have this system, right? X sub I plus 1 equals to AXI plus BUI. You say BUI is equal to minus KXI. Substitute, you get X sub I plus 1 equals to A minus BK XI. Now this matrix has to have eigenvalues that are by absolute value less than 1. You just do pole placement. Make sure that you ask for eigenvalues that are less than 1 by norm. You stabilize discrete system. That's it. So in terms of tools, no difference whatsoever. Just remember what you want to ask. In the continuous time, ask for negative eigenvalues. In discrete time, ask for eigenvalues within the unit circle. Okay. So, you know, by understanding eigenanalysis, you automatically understand how to design control. Now, let's understand where they come from, where discrete systems come from. Expression number 12 is a continuous time system. That we understand where it comes from, like from physics. Newton law, like those differential equations explaining spring damper system, equations explaining you know, electronic circuits, whatever, like variety of ODEs that come from physical sources, at least, you know, from our point of view. So this is clear, expression 12. Now, what if we have expression 12, we can discretize it. What do we mean by discretize it? Well, we can use the definition of a derivative. You remember the definition of a derivative that you studied when you had calculus classes? Do you? Can someone tell me the definition? Limit, right? Derivative of x of t. So what would be? And limit? Great. That is x dot. So if we fix delta as some number, not as something goes to 0, but just some finite number, and we can call it delta t for, to be verbose, I guess. What we get is expression number 13, right? That is approximately equal means, not actually equal, but kind of similar. Be careful about those approximately equal signs, by the way. Sometimes it is not equal at all, right? Just not even close. And that is not just like in some fringe cases, that is in actual practical cases. Like you can imagine, here is this function. For small deltas, this finite difference actually represents it accurately enough, right? But for big deltas, does not represent it whatsoever. So that is a practical situation. Like, that's not very strange. You just your discretization step is just too big. Okay. And actually, like those functions in real life usually look kind of like this. And you can imagine that derivative taken from here to here kind of looks like this, and you expected it to be like this, right? So no, it's like in real life, those approximately equal signs, you need to be wary of them. Okay, so we say x dot is approximately equal to this finite difference. Now, we could also define it as expression 14 or expression 15. The difference is just that in the first case, we kind of look forward. Like we have our current place in time, and we look forward. And we, let me just draw it, I guess. So here's a function. Here's a moment t. First definition is we look forward and we draw it like this. Second definition is we look backwards, look forward, and draw it like this. And the last definition, we look backwards and we draw it like this. All are approximately the same. What I'm trying to say is you're probably used to definition 13 because it just looks natural. But definition 14 and 15 are exactly the same. There's no reason to prefer one over the other. Okay, that's just something to think about. Okay, now we saw how we can approximate the derivative. Now, what we can also do is we can call x and the point of time 0 as x sub 0. X at the point of time delta t as x sub I. X at the point of time 2 delta t as x sub 2. That's just a way to define those things, right? We simply define our x. Let me draw it here. Here's x, right? Here's t. We define it at the discrete points of time. x0, x1, x2, x3, x4, x5, etc. Instead of talking about x of t, x as a function of t, we talk about discrete sequence of x. We can still talk about it as a function of time, of course, but it is sufficient to just talk about its index to define it. Okay, and in this case, derivative becomes even simpler. It is 1 over delta t of x sub I plus 1 minus x sub I. That is the same expression as before, that this definition that you saw. But now we introduced notation, so it became like that. Okay, next. We substitute back into our equation x dot equals to ax. We consider it at the point of time t, which for point of time t, we assume that x is equal to x sub I. Like the closest value of x. I mean, when what do I mean? T, we can represent it as some I times delta t, right? Approximately. Of course, t is a continuous variable, so it doesn't have to be equal to this, something like this. But there will be always a closest I to current t. Like, let's say it is 100, and let's say this is like 100,02. Delta t is equal to 0.1. So we can choose I to equal to 1000. That would be closest I. So you can kind of find the closest I times delta t to any currency. Okay, so we have this AXI, and we substitute instead of x dot this finite difference. Finite difference, let me just reiterate, is when we have a derivative and we instead of it we write next element minus previous element divided by distance. That's what we call finite difference. In this case, x sub I plus 1 minus x sub I divided by delta t. Finite difference. Okay, and we get expression 18. Now, expression 18 is actually more or less a definition of a discrete system. What we can do now is to try to simplify it. So let me try to see if I can simplify it here. So we have 1 over delta t x sub I plus 1 minus 1 over delta t x sub I equals to x sub I. Right? That's the expression 18. I'll move this guy here, and I'll add the identity matrix to the notation, right? Doesn't change anything. So we have 1 over delta t x sub I plus 1 equals to A plus identity matrix times delta t x sub I. That's expression 19. Except in the expression 19, we multiply both sides by delta t. So we get x sub I plus 1 equals to A times delta t plus I xi. Yep. So expression 19 tell us relations between the original expression. Original expression, remember, was x dot equals to ax. This. And our discrete expression, which is this. The relations is given like here. Yes. Dimensions. T is a scalar. Which matrix are you talking about? Delta t is not a matrix. Delta t. No, it is a scalar. It's not a matrix. No, no. Yeah, you cannot consider the matrix as a point. In linear algebra, I understand where you're going through to, but that is just one of the pitfalls of notation, basically. In linear algebra, we use numbers very freely for the sake of rapid learning, right? So we use the same notation for scalars, matrices, vectors, and this creates confusion. Vectors are like elements of specific vector space. But you know, we treat them as same as like we always write them as the columns of numbers, but they are elements of the vector space, right? Okay, matrices are operators. So they basically are objects that transform one vector space into another vector space. But we write them as brackets filled with numbers. But they are operators. And you know, right? Scalars is just the pure numbers. They don't represent elements of linear spaces. They don't represent operators between two linear spaces. Of course, you can have an operator which is just one number, right? But scalars by themselves are not operators. You can have an operator that is just a scalar, but not the scalars are not operators, right? So when what I'm trying to say here is you can confuse the two. So let me just give you one example. So any vector, and I'm sorry for, you know, if we find this a little bit too abstract, but you know, it's good to, if you feel like you understand this topic, this what I'm talking about, just check that your understanding is exactly the same as mine. That is a good exercise, I think. So first of all, like for example, we can say that any vector can be represented in a basis as a sum of scalars times vectors that create the basis. So you have a basis made of vectors, B1, B2, B3. Those are vectors. And you can represent any vector in the span of this basis, like in this linear space, as a sum of scalars times vectors. Those scalars are not linear operators. They're just scalars. They say how to scale the vector. So all they do is scale. That's why they're scalars, right? They don't rotate, don't translate it into different linear space. They just scale. So, but of course, you can have a one-by-one linear operator, which would actually transform a one-by-one linear space into a one-by-one linear space. So a real number line into a different real number line. But that's not what they do. Those guys just scale vectors. They're not linear operators. So yes, we scale it. So let's just look at the expression 18 and 19, right? So expression 18 has a number 1 over delta t. Let's say delta t is 0.1, then 1 over delta t is 10. So it would be 10x sub I plus 1 minus 10x sub I equals to ax sub I. You can divide by 10, right? You can divide by 10. Like you can divide and multiply by scalars. That is because that is this, like you cannot multiply divide by matrix freely, but you can do by scalars. Scalars are commutative. Like you know, you have like those commutative properties, etc. So unless it is 0, nothing changes. Blah blah. So you have this expression number 19, which happens just by dividing by the scalar or by multiplying by delta t, and then transforming x sub I to the right-hand side. Again, shifting vectors from right-hand side to the left-hand side, it doesn't change anything. So, you know, That's what we do. We multiply by scalars, which is a legal operation in linear algebra. We can multiply, divide by them, unless they're 0. And we can shift vectors from right-hand side to the left-hand side. It's also legal. Good, right? If you want, we can discuss after the lecture. Okay. Good. Now, expression 19 is how we get basically our discrete form. It's kind of interesting, right? Notice that you have original matrix from the continuous form times delta t plus identity. So raise your hands if those of you who think this is exactly how it's supposed to be, this is clear, that's intuitive. Oh, quite a few of you actually think it is intuitive, right? That's very surprising, actually, because this doesn't look intuitive, but it is. So let me, just in case, at least half of you didn't raise your hands, so let me explain. So what happens is you have your continuous time growth. Let's say you grow at the rate of like 1 per second. So what you expect at the time delta t is to grow by this 1 per second times delta t, right? Okay, so you were here, you're going to grow over the way here. So this part is just how much you grow over delta t. But you're also not going to lose the progress that you made before. So this constant part, you're not going to lose it. So this is what this is. So you just, let's say I was walking with a velocity 5 meters per second. And I was at the mark 100 meters. This will allow me to keep my 100 meters. And this 5 meters per second times whatever delta t I choose. That is how I get my update matrix. Notice now that if delta t is extremely small, let's say delta t is 1 over million, okay? You have a megahertz, like 1,000 kilohertz frequency. This will be almost identity, right? Can someone identify any problem with that? Just just guess. Yeah, the eigenvalues will be very similar to identity matrix. That's true. Yeah, round off error, right? Yeah, you want to say the same thing, right? No. All right. So yes. Mm-hmm. Yeah. Now, like, if you're correct, let me just add one detail to your answer. So, what is x sub I plus 2 for this expression? It is a times x sub I, right? So after 10 steps, you have a to the power of 10 times x sub I, right? This means if you can have Eigen decomposition, basically it would mean that you'd have, okay, let's forget Eigen decomposition. Basically, this would mean that you'd have this matrix multiplied by itself a lot of times. And eventually the small details that has to do with this tiny a will be lost in the round of error. Everything that will remain will be this identity that dominates. Because like once you multiply it, let's say you have like 1.110 to the power of 10. Just imagine how much of an influence will this one have after like each multiplication. Like after each subsequent multiplication, there will be some influence, but the previous steps will be lost eventually. Okay. So that is kind of like, and this is actually pretty okay, right? It is still, only 3 orders of magnitude difference. But if it was a million, it will be 6 orders of magnitude difference on each step. So this is kind of like, remember your question before? You said like, what is the cutoff frequency? On high frequencies, you start to have this type of problems. So there are a lot of things to consider. Is basically what I'm trying to say. Okay, so this is not a walk in the park. You need to consider the size of delta t in terms of numerical errors. Absolutely a real problem, not something that made up. Good for us. So usually we don't, how should I put it? We find ways to deal with those things. Like that is not a completely horrible situation. But delta t, we don't usually get it like in the million, like 1 over million. Like 1 over 1,000 is more typical. Okay, good. Now, remember I said that we could have different types of this finite difference. Well, let me show you just one interesting way to do the discretization. So one interesting way is to say, let's discretize it with the same finite difference. This is the finite difference part. But we say that it is equal not to this I step, but to this I plus 1 step. So this x dot is equal to a times x I plus 1. If this sounds ridiculous to you, you say like, how the future x influences the current x dot? Well, I can say this is exactly the same as this. And that is legit. This is just another way to find the finite difference. So this was legit, we talked about it. Therefore, this is legit. This is exactly the same expression, but we just shifted the notation by 1. Okay, so this is possible. Notice that the future x is on the right-hand side. So we cannot leave it on the right-hand side. We need to put it to the left-hand side to do anything. How do we do it? Well, we just transfer it here, transfer this here, multiply it by delta t. So what we have is I minus a delta t x sub I plus 1 equals to x sub I. Right. And then we can multiply both sides by this inverse. So we get x sub I plus 1 equals to I minus L delta t inverse sub I. This inverse has to exist. If it doesn't exist, then the expression doesn't make any sense. Like it's not physical if it doesn't exist. So it has to exist. And this expression 21, is actually used in practice. It is used more often with numerical methods for integration. You probably heard of Euler integration scheme, right? At least in your homework, you did Runge-Kutta, right? So Runge-Kutta is fourth order integration, and Euler is a first order integration. Okay. This would represent something like implicit Euler or backstep Euler. There are ways to talk about it. This is actually one of the most stable schemes of numerical integration you can imagine. Runge-Kutta is much more precise. This is much more stable. When I say stable, there is an idea of numeric stability, not of stability in terms of control, but numeric stability. That is when your integration scheme does not fall apart. If when you go home, if you want, try to integrate using Runge-Kutta a equation for a pendulum as a spring damper system, but make the damping coefficient like alien and the spring 1. see if it works. You'll find out what numeric instability means. Yeah, it's fascinating. But this extremely simple system, second order linear equation, will fall apart. So it's very interesting. But using implicit Euler, you can integrate it, and it would just be stable. Everything will be okay. So this is useful. This is useful also because those properties of numeric instability, they have to do with the way you design your matrix. It has to do with eigenvalues of the matrix. Basically, you can say it has to do with relations between the biggest and the smallest eigenvalue, something like this. And sometimes all you need to do to fix the problem is to rewrite it in this backwards way, like this. However, like we are not going to go into this in the class, but I wanted to point it out because I think knowing those things, that they exist, in practice can mean the difference between like staring at the problem and not knowing what to do, and you know, knowing that there is something, finding it in the textbook and solving it. This is also a problem property of mathematics, not of the practical systems. So as a mathematical property, it can come up with your programming practice, even if you never do control in your life, but you work with sequences of numbers that are supposed to grow linearly or change linearly. You can run into this type of situation where is the eigenvalues of your operations that you do are just drastically different, and the whole process becomes unstable. But basically, it is possible to make it stable again just by running this type of procedure. You can notice here there is an inverse. This inverse, you can think about it as a solving linear equation. Of course, like you can do it once, since it is a LTI system. You can do it once. But if it was a nonlinear system, you can still do it. We will just have to do it on every iteration. So you can think about it as such. Like in the normal method, you simply multiply, you get your next step. Like with Rangi-Kata, you get your coefficient multiplied by some step, go forward. With implicit methods or implicit models like this, what you do is you solve equation on each time step, and that allows for some additional properties of stability. Okay, my point here is just to make you acquainted with this idea. It is a very interesting idea, but it's not something that you're going to stumble on naturally. So I wanted to point it out. Okay, let's see what we have left. Now, we just have a few more ideas. So what we did so far was to find out how we make discrete matrices out of continuous matrices. So we have continuous system with matrix A. How do we find the discrete version? Just write A times delta T plus I. That's all, right? You got your continuous equation of a pendulum, of a spring damper, of a quadrator, multiplied by delta T plus I. You got your discrete version. Sounds good, right? Easy. How do you get the B matrix? Multiply by delta T. Why? Can someone tell me why? Oh, because let's just add a B matrix here. What would be the next? Yes. Mm-hmm. No, you just like this guy, when you multiply both sides by it, it will get, you'll have this expression, right? X sub I plus 1 minus X sub I equals to A delta T X sub I plus B delta T U sub I. So notice that this is where you have A times delta T. This is where you have B times delta T from. That's all. Just right-hand side is multiplied by delta T. So of course. Okay. So the identity comes from this guy. A times delta t from here, B times delta t from here. So very, very simple. So expressions 22, 23 is how you go from continuous to discrete. I mean, I hope looking at it, you just feel like easy, like, you know, just give me a second, I will do it. No problem. Because it is easy, right? Okay. And we get our discrete dynamics in the form 24. This dynamics has a name. This is called zero order hold. You'd find this name in the literature often enough, and it is important to recognize what it means. It means that basically you're assuming that for the next time delta t, your dynamic is not going to change. Your dynamic is going to stay the same, like the derivative is going to stay the same. That's what you mean. What it means. So your x dot in real life changes continuously. If we are talking about continuous system, like it changes, right? But you assume that for a fixed number of seconds, it's going to stay the same. That is what our finite derivative assumption gave us. Okay. So zero order hold means that derivative is going to stay the same. Let's look at it graphically. So on the left, what we show is derivative. So on the left and the right, this red graph is a discrete version of the derivative. And the gray graph, I don't know if you can see it, is actual derivative. So zero order hold assumes that it is piecewise constant. The derivative is. Okay. Now you could have a first order hold, assuming that the derivative changes linearly. That would be the graph on the right. We're not going to discuss how to produce first order hold, because to the best of my knowledge, no one uses it in practice. Zero order hold is used all the time. First order hold, I never seen it. But it is useful to get the idea, right? Instead of assuming the derivative is always constant, you assume it is a constant slope, but it changes linearly. Now, there is one thing that actually is used in practice instead of zero order hold, because zero order hold introduces errors. Like it is incorrect. Like after you differentiate, integrate your zero order hold, you don't get the original equation. It's incorrect. Like you can, let me put it this way. You can discretize your system, simulate it forward with zero order hold. If you discretize it with zero order hold, you're not going to get dynamics that you would have gotten if you simulate the original system. It's going to have errors. There is a way, however, to do it without errors, and that is precise discretization. That's the last slide. Sorry for always keeping you, late. Okay, so there is a way to discretize it exactly, and that is the way, 26, 27 expressions. So the way you do it is actually just by solving differential equation. What you're saying is, okay, we had our original system. Where is the original system? Do we have any? Yeah, here. We can simply solve this equation forward, find exact solution. Okay, using matrix exponentials. Matrix exponentials, I don't know if you studied them with Ivan Konyukhov. I don't know, maybe you did. Matrix exponentials is just a shorthand notation for, well, in some ways, for the solution of the equation. But basically, you can solve the equation exactly, and you find the A matrix on this time period. And then you can also try to do the same for B matrix. It is a little bit more complicated, but it's also doable. And that's it. And then you would have slope, which would not correspond to the slope of the system at the point where you try to find the discretization. So, but it would correspond to the slope, which after you simulate it forward, would land you at exact same point where a continuous system would have landed you if you simulated it. You understand, right? So let's say that I'm here at the point 100, And my continuous dynamics would land me in delta t time at the point 100.5. Regardless of what my slope of my continuous dynamics is, precise discretization would give me such a matrix that after delta t, I'll be at the 100.5. It doesn't matter what my current slope is. Maybe my current slope is very high, and if I compute zero the whole, I will be there. Doesn't matter. For precise discretization, will compute the whole, look at the whole trajectory all the way to here, and will give me such a that after one step I will land here. That is the idea. Those are the formulas. You can actually compute it all in MATLAB. I'm not sure if there is a function or if you have to do it by hand, but it is simple. Like this looks complicated because of the integral and because of matrix exponential, but it is not. It is a couple lines of code. So in your practice, you'll be able to do it with a couple lines, and it does make a difference. We did use those in practice. Makes a difference. So don't kind of look down on this precision. All right, that is it for, I think, for the content. Let me just double check. Yeah, here is the suggestions for what to read. And that's it. Do we have any questions before we go to the break and start tutorial? All right. Thank you for your attention. Whoever has questions can come up after the class is over. Now you have a break. No.